point or the operating region or the operating conditions in DC voltage. Means that the quiescent point or the Q point is given or it's established by using a certain voltage and the external components, which are resistors. Usually we may see 2 or 3 or 4 resistors as the RB, RC, RE. All these resistances and the label for the resistances is related with the connection to the transistor. Remember that the transistor, the way it's given, or the semiconductor, the way it's given, cannot be used in amplifiers, cannot be used to gain a voltage. Again, what we are looking for, we are looking actually to place a transistor on a load line. That load line is given by the voltage source, which is the VCE or the VCE max. It's given by the maximum collector current, which is the IC max. And most of the time, and I'm having an example today, most of the time we are looking to place the transistor in the midpoint or the mid of the load line. Means that most of the time we are using to use the transistor in this region. Now, going back to clarify again what means the Q point. Actually, if I'm looking in any of these graphs, you notice that the projection of the Q point on the x-axis, that's the VCE. The projection of the Q point on the y-axis, it's the collector current. Means that determining or finding the Q point of a transistor in a circuit is actually determining the two components or the two coordinates of the Q point, which is the IC and the VCE. Remember that those those external components, external resistances, and the voltage source that is applied to the circuit, or the DC voltage applied to the circuit, it will determine or it will establish the operating point or the Q point. Why it's so important to take or to place the transistor in the midpoint on the load line. And here is an example that explains, what's the purpose of choosing or designing the circuit that has the Q point somewhere in the middle of the load line. Remember that the Q point is established by the external devices and the DC voltage source. On top of that, we are applying an AC voltage source on the base. Means that the input voltage or the base voltage or the base current has a certain value. For example, the base current is between 400 microamps and 200 microamps. As we are applying or superimposing an AC voltage on a DC voltage, remember superposition from ELE350? Instead of having two DC voltages, we have an DC voltage or we have an AC voltage superimposed on an AC voltage. Means that we have the ability of choosing or designing the circuit, choosing the right external resistances and the voltage applied to the circuit to place the transistor in the mid region of the load line. And on top of that, we are applying an AC voltage or an AC current or a variable base current. And in this example shows the swing or the limits of the input or the base current. Suppose that the given or the base current in the Q point, it's about 300 microamps. You notice that I can have a swing on the base current between 400 and 200 microamps. As this AC voltage or AC current is superimposed on a DC voltage, means that superimposing on the Q point or the quiescent conditions, you notice that on the output, I'm having a replica of the input current or the IB, but a larger current, that's the IC at Q point, which can be changed from 40 milliamps to 20 milliamps. In the same time, if I'm looking to find or to determine the output voltage, that's in terms of the current, but in terms of the voltage, that's the VCE at the Q point. That's why you'll see the third index as the Q, means that it's the Q point or the Q value or the quiescent point or the quiescent value. You notice that in terms of the voltage, again, we have the replica of the input signal or the input AC voltage as an amplification or a gain in terms of the current or a gain in terms of the voltage. I explain, why it's so important to choose, the Q point in the middle of the load line. I say, no, it's, right here. Suppose that we didn't choose, the right Q point for a transistor or for a circuit, and this is what is going to happen if we are applying or superimposing an AC voltage on the DC conditions. You notice that in this example, if I'm applying, input voltage or an input signal that swings, outside of the active region, you notice that this part or this peak of the input voltage, it will be clipped. Means that I'm not having, the full waveform of the input signal, means that the output voltage or the output current or the output signal, it will be clipped. That's why it's so important to choose the Q point somewhere in the middle of the load line. Suppose that I'm choosing, the same transistor, the same circuit, but somewhere, closer. Suppose that I make, the Q point, at this value. At this value, you notice that I'll have, the same situation when the signal actually is clipped, but on the upper side, means that the limitation of the saturation current or the IC max. Means that in both cases, if the transistor is not placed on the right spot or in the middle of the load line, the limitation is the input. The limitations will be in the input signal or the base voltage or the base current that can be applied to the transistor in order to have a similar waveform or a replica of the input signal without having a distortion. This, clip signal output voltage or the output current is in terms of the distorted signal, which kind of looks like the input voltage or the input signal, but some portions or some of the positive or the negative waveforms, it will be clipped or it will be altered from the initial or from the applied signal on the base of the transistor. Now we'll focus on biasing and we'll discuss three basic configurations. That's, the three basic configuration. Most of the time you will see a common base, common collector, and the common emitter. You notice that all these three configurations has a common word in it. Now, let's try to clarify what means a common. If that's, the input loop and that's, the output loop. You notice that the common connection is the base. That's the common base connection or the common base circuit. The common refers with the terminal that is common on the input and on the output. Some, characteristics. But again, I'm not going into details. I'm just showing, some basic characteristics or properties of the common base. You notice that the base is common on the input loop and on the output loop. Has a very low input impedance, very high input impedance. The gain is almost 1. I mentioned that we are making one of the three approximations that the IE is the same or is equal to the IC. Means that we are not gaining any current, but we are gaining, some voltage. Has a very high voltage gain. The common collector. Again, suppose that I'm connecting, the collector into the input and into the output loop. Means that the collector is the common connection between the input and the output. Has a very high input impedance, very low input impedance, which gives you an idea about, the applications of this type of connections or this type of the circuits that may be used. Most of the time it's referred as the emitter follower because there is no gain in voltage. The voltage gain is almost 1, but has a very high input impedance and very low output impedance. Now, suppose that you are designing, a circuit and the two sub-circuits, the input and the output, has two different impedances. The question is, what can we do to match, those two impedances? Remember, we talk about the impedances and the matching impedances in ELE105 when I introduced the maximum power transfer. In order to keep, the maximum power transfer from one circuit to another circuit, or from a voltage source, or from an input voltage source to an output voltage source, or from an output circuit, we have to match those two impedances. If the impedances are not the same or does not have, the same values, the power transfer is at the minimum. That's why in circuits that requires different impedances, like low to high, or high to low, and so on, we are using an emitter follower. It doesn't do anything in terms of the gain, does not amplify the circuit. It will just match the impedances between two sub-circuits. The most common one, and we'll focus on the common emitter. You notice that again, common emitter, or the emitter is common on the input loop and it's common on the output loop. Most of the time you will deal with the common emitter because has a very low input impedance, very high output impedance, and has a very high gain in voltage and in current. Again, means that most of the time, I'm not saying always, but most of the time, most of the circuits are a common emitter. Some applications, as I mentioned, requires a common collector. Some application requires a common base. But we'll focus on biasing a common emitter, and that's why we'll discuss in details how we can determine the Q point of the common emitter circuit. the first circuit that is used has the simplest circuit has some advantages and disadvantages. You notice that uh, the notation for the base or the voltage that is applied on the base and the voltage that is applied on the collector. The VCC, it's a double subscript. It's used for the voltage that is applied on the collector, and the VBB, it is the notation, or it's the label for a voltage that is applied to the base. Remember that I have to have those conditions in order to have to place the transistor in the linear region or the active region. The base emitter junction must be in forward bias, and the base collector has to be in reverse biased. Knowing that two conditions, we can use two different voltage sources. One is used to place the transistor to supply voltage to the base in order to get the base emitter voltage as the 0.7 and the other voltage, which is VCC. The question is why it use a double subscript. Yes, if you remember in the first slide, we mentioned that this point can be labeled as the VC, which is the collector voltage with respect to ground. You notice that again, it's a single subscript, and the convention or the rules for a single subscript is that the voltage is measured always with respect to ground. The other voltage, at the base, that's, the VB, or the voltage at the base, I will label that as the VB. And we have to determine in some questions, in some examples, what is the voltage VB, or the voltage at the base of the transistor, again, with respect to ground. You notice that this, in this case, the VB with respect to ground is actually the 0.7 volts, which is the VBE. Again, why it's the 0.7? Because the base emitter has to be in forward bias, and the VBE voltage is the 0.7. In some other circuits, it may require to determine the VE. Again, it's a single subscript, is with respect to ground, and in this circuit, the VE is equal to 0 because it's connected directly to the ground. Now, let's have a look on how to approach or how to determine the Q point. Again, what we are looking for the Q point. I'm looking for the IC, that's, the IC. And we are looking for the VCE, the two components, or the projection of the Q point on the load line. And that's, the VCE. You notice that it's a double subscript, means that it's the voltage between the collector and the emitter. Now, to determine those two components, or those two characteristics of the Q point, we have to take, the approach of using the KVL in the input loop. That's, the input loop, and we are applying the KVL in the output loop. I will label that the two KVLs. There is nothing to be memorized. It's just a different notation that it's used in electronic devices and circuits, just a different notation in terms of the RB, resistance that is connected to the base, RC, resistor that is connected to the collector, and the RE, we'll see a bit later, resistor that is connected into the emitter or to the emitter of the transistor. Now, in order to determine the IB, which is the current that flows into the base, that's, the IB, or the base current, we are applying the KVL in the input loop. And that's, the VB, or the supplied voltage, the VBB, minus the 0.7. You notice that, again, the base emitter voltage, it's a 0.7. Again, that's, the voltage VBE. Applying the KVL on the input loop, the VBB is the VRB, which is the voltage drop across the base resistance, plus the voltage VBE. 3 volts minus the 0.7 divided by the resistance that is connected to the base makes, the IB as 10.45 microamps. Another equation, or another new equation, that is in terms of the relationship between the IB, that's, the IB, and the IC. The IC, or the collector current, which is the same with the emitter current, is the beta IB. Beta is given. Most of the time, the beta is given or is provided in the specs of the transistor. And in this example, beta DC, or simply beta, is 200. And we are multiplying the gain in current. That's, the beta, 200 multiplied by the base current, 10.45, makes, the collector current 2.09 milliamps. Means that one of the two components for the Q point of this circuit, of this transistor, that's, the Q point, is the IC, and the next one is the VCE. Again, applying the KVL in the output loop, or in the collector loop, we can find that the VCC is the RC minus, or is equally the VRC plus the VCE. From this equation, we can determine the VCE is the VCC, or the applied voltage, minus the drop voltage across the collector resistance. I will label that as the VRC to avoid any confusions between the VC and the VRC. Again, pay attention for those details. VRC is the voltage drop across the resistance connected in the collector of the transistor, and the potential, or the voltage at the collector, it's with respect to ground. Means that the VC is the potential at the collector of the transistor. The VRC is the voltage drop across the resistance that it's connected into the or to the collector of the transistor. And it's 15 minus, that's the RC, ICRC, which is the VRC. Means that we subtracting from the supplied voltage, and the VC is 8.1. Means that the two coordinates of the Q point is the collector current 2.09 and the VCE as the 8.1. The question is, how we can determine if the transistor is saturated or not? Again, the two notations, sometimes you'll see the IC set, the saturation on the collector current, or simply the I set. I'm making the assumption, but keep in mind that, and I put that in underline, for this example, we are using the VC as 0.2 volts. And I use, in some previous examples, just to show you, the real value of the VCE. In our calculations, we are assuming, the VCE as 0, because again, the VCE is much smaller than the supplied voltage. I mentioned that the VCE is anywhere between 0.1, 0.4, 0.5 volts maximum. That's, a very small voltage between the collector and the emitter when it's saturated. Means that we are comparing, the VC with the supplied voltage, 5 volts, 10 volts, 20 volts, or, in this range, which is at least 10 times smaller. Means that in our calculations, we can neglect the VC saturation, or we can make, the VC saturation as 0. In this example, I'm choosing again the real value as the 0.2 volts, and is 15 minus the VC over the RC, which makes the saturation current, or the maximum current that can flow through the transistor in this circuit, as 4.49. Now, the IC that we just determined is about 2.09, means that I'm placing this transistor closer to the, or in the mid-range, or the midpoint of the load line. Another question is if or find the cutoff voltage. Remember that, and I'll go back to the main diagram. That's the cutoff voltage. Now let's try to clean it up a little bit. On this side, if I'll try to clean up a little bit, this diagram, you notice that on the cutoff region, or the cutoff voltage, and how we can determine that. You notice that the cutoff region is defined as the region when there is no current applied to the base. If there is no current, or the IB is 0, the IC is 0. Means that there is no current on the output loop, or the IC is equal to 0. In this diagram, if the IC is 0, there is no voltage drop across the RC. Means that at the cutoff, or suppose that I'm removing, this connection, means that the IB is equal to 0, IC is 0, means that the VCE in the cutoff is the same, or is equal to the VCC, or the supplied voltage. Remember that the cutoff, or the transistor, is in off state. There is no current that flows between the collector and the emitter. The notation that you may see, the VCO, or the cutoff, or the base current, is equal to 0. Means that is the same, or is equal to the VC, which is the 15 volts. Now, going back to this circuit, I said that, advantages, it's very simple. And by simply adjusting the VB independently and the VCC, we can change, or we can modify the Q point. That's probably, very convenient. If we have to adjust, the Q point, suppose that the IC and the VC has to be moved, towards to the saturation, or towards to the cutoff, by simply adjusting just the VBB or the VCC without changing the value of the two resistances. What is the disadvantage of this circuit? Uses two voltage sources. Not always are available two voltage sources. More convenient is connecting the RB, or the resistance for that is connected to the base, to the same voltage source, and we'll end up with a simplified circuit that uses just a single voltage source, 5 volts, 10 volts, 15 volts, and or any other voltages. But I'm using, just two resistances. This type of circuit is not used intensively, and I'll refer, a bit later, because it's beta dependent. You notice that I'm applying, again, the KVL on the input and the KVL on the output. There is nothing changed on the output. The output stays the same, the VCC, RC, and the emitter connected to the base. And from the previous equation, instead of having the RB, you notice that in this equation I use the VBB, But instead of using, the RB and the VBB, I'm using the VC and the RB. That's, the only change. Means that I'll follow, the same rules and applying the KVL in this input loop and applying the KVL in this output loop. Now, in order to determine what is the IC or DIB, the same approach. And in this example, suppose that the beta is given as 50. Again, that's, the beta or the beta DC as 50. You notice that is dimensionless because it's the ratio of the two currents, the IC over the IB. To determine the IC as the beta IB. But we know that, to determine the IB is the VCC minus the VBE. That's, the voltage between the base and the emitter divided by the RB. And making, the calculations will determine that the IC is equal with the 8.404 milliamps. Most of the time, the value of the RB is very high in terms of few hundreds, like, 100, 200, 300 kilo ohms, which makes, the current that flows through the base a very small current. To determine the other component for the Q point, you notice that find the Q point is very convenient of finding, or instead of say finding the IC and the VCE, is find the Q point of the circuit. The VCE, or the voltage between the collector and the emitter, is the VCC minus the drop voltage across RC. You notice that, again, there is no difference in the equations from the previous circuit, and we'll end up with a voltage as 10.35. Now, the inconvenience or the disadvantage using this circuit is very simple. It uses just two resistors, but is a beta dependent. Why it's, beta dependent? Now, suppose that the beta is given for 25 degrees. Remember that as the temperature is increased, that's, an external energy, the electrons becomes more agitated, and it will increase the beta, or the amplification or the gain of the current. And I put that in writing, as the temperature is increasing, the beta is increasing. If the beta is increasing, and look at this equation, that's the relationship between the IC and the IB through the beta of the transistor. As the beta is increasing, it will cause an increase in the IC, which will drop the voltage between the collector and the emitter. Dropping or lowering the voltage between the collector and the emitter, the Q point moves towards to the saturation. Means that if we are making, all the calculations for a certain IC and the VC closer to the midpoint of the load line, increasing the temperature, it will affect, or it will change the Q point that we calculated at 25 degrees. Means that is not an ideal circuit, but is very simple. In order to overcome this inconvenience, I said that is beta dependent, or depends on the temperature or the ambient temperature of the circuit. A resistor is added into the base of the transistor. You notice that using, the same circuit to compensate that change in the beta, or change in the VCE, a small resistor, usually few hundreds or few tenths of ohms, it's connected into the emitter of the transistor, which makes an emitter feedback bias. Again, that, emitter feedback is referred to the resistance that is added into the emitter of the transistor, which will compensate the change in the beta as the temperature is increased or decreased. Now, this type of circuit has a different approach. The approach is, first of all, we have to determine what is the current that flows through the circuit to determine the IE. We know that the IE is the same with the IC, with the current that flows, into the collector. And once we know the IB, or sorry, the IC or the IE, we can go back and find the IB. Now the relationship, and that's the equation that it will be given for this circuit only, and pay attention for that. This equation is given and can be applied only for this circuit with a resistor connected to the emitter of the transistor. Now we may simplify and we may see a different look of this equation, but is the same equation. And you notice that I'm having a fraction and another fraction on the denominator, and this is what I'm trying to simplify the denominator of this main equation. And the other equation actually is rearranging the equation, and if I'm multiplying the RE with beta, means that I can write a single denominator as the beta RE plus the RB, and beta move it on the numerator of the main fraction. Means that the equation that is given, and that's much easier to be used, is the RB beta RE on denominator and the beta VC minus the VBE on the numerator. Again, the approach is, the first step is finding the IE using the given equation. Once you know the IE, we can determine what is the IB, knowing the relationship between the IC and the IB. Once you know the IB, we can determine what is the voltage across RB, what's the voltage across RC, knowing the RC, and so on. Means that the first step in this type of problems is finding the IE. Again, this approach is specific only for this type of problems. And that's, the example that I made. I'm finding the IC, but remember that the IC is the same with the IE. That's one of the 5 useful equations. Once you know the IC, we can determine the VCE, and is the VC minus the drop voltage across RC minus the drop voltage across RE. Again, looking in this diagram, let's try to clean up, this diagram a little bit, just to show the KVL. KVL in this output circuit now has the drop voltage across the RC and the drop voltage across RE. In top of that, we have, the VCE, means that to find the VCE, the voltage between the collector and the emitter, which is the VCC minus the VRC minus the VE. The addition that is in this circuit with previous 2 circuits is that has the voltage drop across the emitter resistance specific for this circuit. Now, doing the calculations, we'll end up with 4.16, and you may have some other questions, but remember that the VE, it's the voltage at the emitter, and I introduced this notation from the first or lab or from the beginning of this course. VC, the potential at the collector with respect to ground, and the VB is the potential at the base with respect to ground. Now, those are, the equations. The emitter current multiplied by the emitter resistance. The VC is the VCE minus the VE, or there is another way of finding the VC as the VCC minus the drop voltage across the RC. Means that there is no difference in how we are applying the KVL in the output loop. And for the VB is the potential at the emitter plus the voltage between the base and the emitter. Means that the emitter voltage plus the VBE, which is the 0.7. Most of the time, and that's, a bit more convenient circuit because gives you, some flexibility of simply adjusting a single resistor, and we are ending up with the Q point from a circuit or for a circuit that can be moved easily by simply adjusting one of the two resistances. You notice that this circuit, it was again used in the first lab, in the second lab, just to get used to this circuit. Now is the time to explain and see the approach. I mentioned that for the first circuit or the first calculations, make the assumption that there is we have no idea about the transistor. Now we know that the base current is very small in terms of few micro or few tenths of microamps up to probably 1 milliamp or 2 milliamps, no more than that. In order to have the R1, R2 connected in series, which will act as a voltage divider. That's why I make the assumption that the IB is very small compared with the current that flows through the R1 or I2. Remember, the condition is if one of the two currents, one of the two voltages, one of the two powers, it's 10 times less than the other one, can be neglected. In order to have this condition means that I have to make sure that the IB is at least 10 times less than the current that flows through the R1 and R2. Why it's this condition, or has to have this condition? Because the IB will not affect actually the current or the voltage that is dropping around the R1 and R2. Means that if the value of the IB is low enough, means that we can apply the voltage divider rule to determine what is the voltage at the base of the transistor. The condition is the I2 much larger than the IB, or in reverse way, the IB much smaller than the I2. Now, sometimes you'll see a notation or a condition or as a voltage divider being a stiff voltage divider or a stiff circuit. What that means, the IB much smaller than the IR1 or the IR2. In this condition, or having this condition IB much smaller than the I2, we can apply the voltage divider rule to find the VB. But you notice that the VB is actually the voltage across the R2. Now the R1 and R2 are connected in series. I can apply the voltage divider rule to determine the VB, the R2 over the R1, R2 VC. Once you know this voltage, we are subtracting the voltage between the base and the emitter, and we are finding what is the voltage at the emitter. Knowing the RE, we can determine what is the current that flows to the emitter, and once you know the current that flows to the emitter, we can determine what is the VC. Means that there are two steps. One step is finding the VB. Once we know the VB, we can determine the VE. And once you know the VE is determined, we can determine the current IE, which is the same with the IC. In this example, I make a note for the VC as 1.3 volts. And I said that is not so ideal. And you can answer, the question why it's not so ideal. You notice that it's a very low collector emitter voltage. Means that going back to the main diagram means that the collector emitter voltage probably is at this point, which makes probably a current, I will say, or the Q point probably around, this or it's closer to this saturation region, which is not so ideal. That's why sometimes he's asking, to determine if he's in or closer to this saturation, closer to the cutoff, the mid region, or in the saturation or the cutoff region. Tomorrow, as I mentioned yesterday, we'll have some in-class examples. Basically, we are going over the 4 different circuits, and I will make some like in-class examples for tomorrow. Any questions, comments, concerns, please? If you don't have any questions, have a nice day, guys.